All right. Thanks for joining us. I'm here for my PhD progression talk about the new data types I've been working on for quite some time now. First of all, rough outline. So I will start with why am I doing this at all? Then how was the history so far? What is the status quo now and how do I actually use it? And then what are my plans to expand on this in the future towards the end of my PhD? So first of all, what is a binder in general? So in PLT papers, you often see just some syntax, and it's just implicitly assumed that everyone knows that once there is a lambda in there, it is assumed that people know that this means that actually this X will somehow appear in this E, and everyone knows what is meant. So that this X is in E, and outside it is not there anymore, and you can fill it like a placeholder. We also have some other assumptions usually, and that is the names of the variables should not really matter as long as like the structure is the same. So if no matter if I choose X here or Y, they are the same function. And the other thing is we need to be a bit careful when we are actually doing this substitution. So if we just naively put the Y instead of the X there, what we end up is with another function. It is not the same as we had before. So that is what we want to avoid when substituting. So what we need to do in such a case is we need to rename this outer variable, this Y, so it does not capture the new thing we substitute in, and then we get something that has the same structure as before. So the goal of the automation is to give you all of that for free, basically, with some nice theorems on top to make proving stuff easier. So what I assume you already know, I know you know some function. I assume you know some functional programming, and I assume you know what the simply type lambda calculus is, because it will be the guiding example later on. But other than that, you should not need to know anything. So first of all, I'm doing this in Isabelle, which is a theorem prover. So how does Isabelle look like? So this is Isabelle code. You can think of it as a functional programming language with extras. So we have data types, and Isabelle inherits its syntax from the ML family. So it's not like in Haskell where the type constructors before its arguments. So CA, it is behind it and is written lowercase. Then you have normal functions. The weird thing is you need to put like the expressions in quotes. That's just the syntax. You can omit the quotes if it's just a single lexeme. So in case, for example, here it's just a single A. So we omit the quotes. And the nice thing is we have also some proof automation. So we can state some facts. So this is just a Boolean basically, and we can prove that this is indeed always true by using tactics. And Isabelle has quite good and powerful proof automation. So lots of the part of the proofs are automatic. We don't need to do them, and you will see that later on how we can use the nice automation. What is interesting though is that while this looks like normal syntax from a programming language, none of these things actually exists in Isabelle. So data type and function, the commands, they are not part of the Isabelle core language. They are something that is built on top of that. But for the user, it does not look like that. And that's exactly what I've been doing. I've been working on a new data type command that can help you with that. So first of all, why am I doing this at all? So my personal motivation is I want to get proper record types into Haskell. So the approach to do that is to formalize system FC, which is Haskell's intermediate language, also called core, and then extend this language, which is a simple functional programming language, with these row types that allow me to get proper, nice anonymous records and variants. And then I want to prove that this is still sound in Isabelle. So there's some, this is just how this will be the inspirations of this system. So for this, the important part is I need to prove stuff in Isabelle. So I had a look before I started the PhD, even before I started my master's. how can I do this? How can I do proofs about programming language in Isabelle? And the status quo there is nominal too. It's a package. It's was written by Christian Urban and Cesare. And it is available in the archive for nominal proofs, so it's very easy to use. That's a plus. And it also provides this quotient type, so that indeed variables names do not matter as long as the functions are the same. So quotient type you can see as basically a type of a custom equality that says multiple types are equal even if they're not syntactically equal. It gives you these nice induction principles that avoid variables so that you can have easier proofs. It's of course complex binders like you have in a LAIV expression where they are bound recursively in each other. But the problem with nominal 2 is in the last 3 points, you can define functions on these data types. The problem is you need to do a lot of proofs on them. It's very annoying to do those proofs. And they are not compatible at all with normal. You saw in the slide earlier, the data type command, you cannot use those data types within one of these data types. That also means all the proofs that someone has already done about these normal data types are lost to you because you have to introduce all data types at the same spot yourself. So you can't bind a list of variables and then you lose all the theorems about lists in the Isabelle standard library, which is really annoying. So it's not composable, it's not modular. So the big new thing is that what I'm been working on is the modular approach to binding data types. And this is not as interesting for many people, but with the new approach, we can also express types that are not finite. So not finite, but infinite types, streams that bind variables. Yeah. So what has happened so far? I started my master's in October 2021, and during this master's thesis, I learned actually how to automate stuff in Isabelle, which is happening in ML, in standard ML, and I wrote the composition algorithm that takes two data types, or takes multiple data types and composes them to a big new one, which is, you will see later on how this is used. From May to July, I was part of Tobias Nitko's chair in the TU of Munich, where I then integrated existing code from another master thesis that implement basically the data type construction, and I implemented the recursor, which is a fold on the data type. So my code will give you now a fold on your syntax that automatically renames the variables out of the way. So then we come to now the actual PhD, which I started in September. It's with James and Urian. And during that time, I implemented the variable for variable substitution, the term for variable substitution. These are both basically special cases of this fold. So it's one particular instance of the fold. Variable substitution is the easiest such instance. Term for variable substitution is a bit more complicated, but yeah, same idea. And I've been working on the high-level syntax sugar. So those who know, earlier this year I gave a talk about how this works internally. I will not talk about the internals at all today, because now I'm at the point where I can actually abstract that all away, so the user doesn't need to know how it works. I also added a binder induction method, which we will see later in the example, which makes proofs a lot easier because you can just avoid arbitrary things, which that means we'll also see later. So now we come to the now. How it is now becoming something you can actually use. It's starting to become something you can actually use. So how do I actually use it? Let's go back to simplified lambda calculus. So I just took these definitions from a lecture slide. So this is something you will see in a normal paper. You saw this earlier when I explained what a binder is. And now we want to translate this to Isabelle, where we can do then formal reasoning on this. So the types, they don't bind any variables. So we just use a normal Isabelle data type for that. and the definition looks very similar to the one you would write in LaTeX. The only thing is we explicitly say, okay, this will be the index notation for this constructor. But other than that, same thing. The expressions are a bit more interesting. So here's the new stuff. So the paper just says this is a meta variable, but doesn't specify what type. So I will do the same. I don't specify which type I will use for variables. I can use strings. I can use natural numbers. I leave that open, doesn't matter. So it is either a variable or it's a lambda expression where this is now explicit. As I said, in the paper, people assume you know this, but here's explicit. So this x, this variable is now bound in here. And we have applicational, we have literals, and we have addition, which can also write as a plus, and this unit constructor. So you see, this is a very one-to-one correspondence. And I can also show you how this looks in real life. So here we are in Isabelle. And yeah, this is running code. So here's the data type definition. The thing is, I have not yet written that parser that takes the nice user-facing syntax and parses it. So for now, I'm playing parser myself and do this here. So this is just basically parsing all the constructors into this structure and then calling the function myself. Once I have the parser, this is all hidden just like normal data types. So what does this give me? Now I get what I expect. I get a function that already that gives me all the three variables in the type. That's already something that nominal 2 does not give you. You need to define this yourself, which is very tedious because there's only one correct definition of this. The other thing it gives you variable for variable and here variable for variable and term for variable substitution. Again, two things nominal 2 does not give you for free. You need to define it yourself. And as I said, defining functions nominal 2 involves a lot of proofs. All right. The last thing it gives you is nice induction theorems. So compared to the normal induction theorem, induct. This is a normal induction theorem. If you compare this to the other one, you see there's a new assumption. So we are, for some set that is bounded, so it needs to be smaller than all the values. So for some bounded set, we will give you in the lambda case, in the case where we actually bind variables, we will give you a variable that is not in that set. So with this, you can just avoid arbitrary things. So you can say, if I need to prove something, we will see later, where I have a context that contains variables, I can just say, hey, this new variable should not be in that context. That will make my proof a lot easier. So, but going back to the slides, now we want to do reasoning on this. So again, this is just taken from the same lecture notes paper. This is an inductive definition of a typing relation. So integers, literals are always integers, the same as unit is always of type unit. If two things are integers, then the addition is also an integer. If this variable is in the context and gives this type tau, this variable will have type tau and so on and so on. Again, we can translate this one-to-one to Isabelle. You say inductive, you use the inductive keyword to add a new inductive definition. I call this now type or the typing relation. And again, added the same syntax that is used here in the paper. And then the first case, let's start with the variables. So here we look up the x in the gamma, and if this happens to be the tau, then we assign the type to the variables. The lambda expressions here, right next to it, a bit more complicated. So here it's assumed implicitly that this x is not already in the context. But we make this assumption explicit here. So we say, okay, yeah, it's not allowed to be in the first component of this context. But then if we extend the context with this new type, and this is well typed just like here, then the lambda without the extension is well typed as well. And we can continue with that for all the other cases as well. So just take, here's the literal case. We don't have any assumptions, so there's no pad error here. Just any literal n is of type int. And same with the application. If the two are well typed, then the application is well typed. So this is again a very one-to-one correspondence. And in fact, Isabelle can give you something like this in LaTeX from this. So you don't need to duplicate your code with that. And yeah.
In the lambda rule, if you didn't have x, if you didn't write with x not in first, blah blah blah, would it still be valid?
Yeah, sure. That's well. That depends on what you want to prove.
Jan, this is the internet
speaking. In this
speaking.
case, they meant that it should be distinct, so I added this.
Yeah, okay.
Jan, can you hear me?
So that's just a tuple here. That constructs a tuple, and hash is cons on lists. So it cons is this thing onto the list of the context. So context in this case is just a list.
Yeah.
So what does it? Well, first I can show you this as well in Isabelle itself. But this is just what I showed you. The lookup function is goes through the list and searches for the element, and this thing is just copy. This is literally a screenshot of what is here.
Just comment from this particular question.
Sorry. Okay. Yeah. Question was if this is necessary, if this is somehow enforced that this has to be here. No, this was a choice on my side, because I thought this is assumed to be implicitly distinct, a fresh variable in context. Often there's here like a side condition that x is not in the free variables of this.
Yeah.
But in this case, they didn't do that. So then again, this was the lecture notes. So there's some to see it, how it works. If we read this from the bottom, if we want to prove that this term in the empty context has type int, we can apply these rules, and at the end we have no assumptions anymore. So we have concluded that, and we again can do the same thing in Isabelle. So we write out this this term. So it's an application of a lambda with a literal, and in the lambda we add a variable to another literal. So the outmost thing is application. So as in the slide, the first rule that is applied is the app rule. So let's apply the app rule. And you see then it splits in two, just like here, it splits in two goals. And we can continue from there. So I won't type out the whole thing, but I have the whole thing here. So if you just look through this, so first we apply application. So now a lambda is outside, we are at the rule for lambda. So then, as I said, we had the first condition, but yeah, x is definitely not in the empty context. So that is very easy to solve. So simplification does that. The next thing is we see it's an add rule. So we take the rule for add. Then we have a variable. And indeed, if we look up x in this one element context, that happens to be an int. So that is also solvable. And then literals are always integers. Literals are always integer. Done. We have proven that this is indeed well typed, this expression. So the exact same thing as we had in the LaTeX version. So before talking about the future, I wanted to show another example and a bit an interesting proof. So first here, this says that the introduction rule, so all of these rules should be made available to the automation from Isabelle. And this is now what we want to prove. This is a very interesting, well, it's not interesting, but it's a very helpful property. So if something is well typed, and I take all the three variables of this expression, and if for all the types, if it is in the original context, it is also in some second context, then the second context assigns the same type to that expression. Just like we can the only thing about the context that matter is the three variables, which is a useful thing to have, because it allows us not only to shrink the context, but also to expand the context in proofs. So we can prove this by induction. So let's do this. We can prove this by induction, and we want to do this on the typing derivation. So Isabelle then gives us this auto-generated case statement, and this is similar to what we expect. So the assumptions are now things we know, and we need to prove now the goal. In this case, we don't have an induction hypothesis, but here, for example, we do. So if we know it, if we can prove the assumptions for E1 and prove the assumptions for E2, and we get the assumptions for the whole thing, then we have to prove it for the whole thing. This works out quite well. So in case for variables, because we set up the automation to know about our typing rules, we can just say, hey, try to prove this. Oh, auto found a proof. Nice. And in fact, we can do this a bit shorter. We just remove the whole case because then it falls through till the end. And in the end, we say, okay, auto solve everything that we haven't solved yet. So we can remove just cases that are easy. Oops, here. And you see, it's not, there's no squiggly line. It still is provable. So this is the same. It's also another easy case. This is another easy case. So we only basically are left with the one interesting case. Again, because of the Isabelle proof automation, it was done all for us. The problem now is with this proof automation. If we look at our introduction rule, so I put this here again. We want to prove something in the form of gamma prime implies a lambda. So we will have to go through, this one. So we will have to go through this, our introduction rule, which requires the context, in this case, gamma prime, this x not being gamma prime. What we don't notice, we only notice x is not in gamma. And at this point, we are basically stuck. We would have to work really hard to get some x that is neither in gamma nor gamma prime, and then say, okay, we can rename them, and yeah. But we actually don't have to at all. We can use this, as I said, binder induction method. Binder induction, and we need to use another, so let me just go a bit down. I set up a better inductive rule. So this is not done yet from the automation. That's why there's this sorry and this extra thing here. This is to be automated, to be finished. So I have started working on it. But once we have set up this better, nicer induction rule, you see again, here's this, we can promise this x is not in some set, which is then exactly what we will use. We can have the same theorem again, now use binder induction on this thing. And we want to say we want to avoid gamma prime, because now we will get an extra rule here in our lambda case. Hey, x will not be in the first element of gamma prime. And with this, the whole proof is very easy, because this is the first assumption we need to prove. Again, auto found a proof. Then, as I said, this was the one we couldn't prove before. But now with this extra assumption here, that is trivial because it's literally just the assumption. And then in the end, using the introduction rule, again, Isabelle automation has no problem finding this. Same here. This was this proof. Another thing how the automation helps you, just say apply. This is Sledgehammer, which tries a bunch of automated theorem proofs, so for example, CDC4, and they get a bunch of theorems and your goal, and oh, okay, I found another proof. So in this case, contact, okay, because I already proved it, this is stupid. because I need to abort this earlier proof. So it thinks this proof is true. We need to say, oops, we were not able to prove this. And then it will find actually a proper proof. Yeah, now it works a little bit harder, but the proof I had there, yeah, vampire, another automated theorem prover, found a proof, and in a second it will give me a nicely compacted Isabelle proof that I can just click on. Yeah, there's the same proof as I had earlier. So now I can cancel this, don't need another proof, click on it, boom, proof is done. So first of all, I was able to get rid of all the boring cases in the proof by just using auto down here. Second of all, the complicated case was not complicated anymore because I got this extra assumption for free without having to do anything. And again, Sledgehammer had with the intermediate steps and the proofs. So there was no brain power involved at all. For these statements there, I literally just took whatever is here, which I need for my induction predicate, copy pasted it, and that, okay, try to prove me this as a step in between. All right, I will just quickly look if there's anything in the chat. No, okay. So this is how it works at the moment. There's some rough edges. Binary induction works usually quite well, but there might be some kinks in applying it. As you saw, the binder inductive that gives me the better induction theorem for my typing relation, that is still very much work in progress. That's what I'm working on right now. But the proof I already have, so I can manually do the proof of that theorem. It's not automated yet. So what are the plans on the future beyond that? So for this July, that's the deadline for Popper 24. We will, Dimitri and now most likely Andre and me will write a paper or submit a paper to Popper about all of that, the new binder induction method, the binder inductive, and the implementation on total, which is fitting because the theory behind the internals are a paper by Dimitri and Andre and others from Popper 19. So it's just now after 5 years, there's a usable thing, not just the theory. Then after that, for either next ICFP or the Popper after, I want to formalize now to go towards my PhD for my topic. I want to go for a history of System FC formalized. So there has been a bunch of extensions to System FC that has to use from the first incarnation to first kind polymorphism and then dependently kinded types and some others. I want to basically start from the smallest one, extend it, and always prove basically progress preservation and the soundness of all of these incantations, because they are all just pen and paper proofs in PL papers. Then at some point after that, I want to, as you saw, I have implemented the fold on the data type, but for co-data types that could be implemented, I need an unfold, which is the dual of the recursor, the co-recursor. So I want to implement that because that would give us Böhm trees, in case you know what that is. So this would be a nice paper because there's currently no theorem prover that has any support for co-data types that bind variables. So that would be a first. And Böhm trees are useful to prove properties about programs, especially in a lazy context. And after that, I want to use all my automation and build on basically the latest version of System FC I formalized earlier and extend this latest version with my row types. And again, prove soundness, so basically extend the latest version, prove that again. And after that, in the far future, if there is still time, so that would already be enough. If there is still time, I would really like to implement this practically in the classical compiler to have working row types in Haskell for the first time in ever. Yes. Can you give a flavor how these freshness assumptions are generated? Yes. So the key is here this binder inductive thing. So if we take a look at this at the normal induction theorem, we see okay, assuming you have the inductive predicates, you have a bunch of rules, and you see that for lambdas there's nothing special here. It's just what the user written. So binder induction, this command takes this normal induction theorem and improves it. It requires some input from the user, mostly about equivariance, which means that, for example, this function, if I rename the variable here and rename all things here, that is still the same thing. So the user needs to prove that for all the functions that are involved. And what comes out is this theorem.
Can you hear me? Can anyone hear me?
This is the most general form. So this has, instead of the static, so I showed you earlier this.
I can hear you, Jamie.
Well, can I be given the speaker,
on
please, so I can respond, please?
But I'm also not there.
I called it.
Oh, lost. So
this
it's
has a
you and me
static
stuck in
set here.
cyberspace, is it?
That's not the most general
I think
form.
so.
There's actually the same form for this one, which has a function here, because this allows it to change during the induction, which is
Well, I can't do
needed,
this.
For example,
I can't type this. I'm on a
context, it
tablet.
changes in the lambda here. So
Okay, but I saw a question that you gave in the chat, but
Yeah, it took me like 5 minutes
in
to
this
type
case,
it
the
out.
context changes.
what question do you want me to type out?
To catch also those
He
cases,
said you get it using equivariance, but equivariance is a hard bit.
Induction theorem, and this basically
So
generates an
if they
equivalent
get
one
the freshness
for a,
assumptions
typing
using
relation.
equivariance as
If-
proved by the
and if
user, they're
all
giving the hard bit to
of
the
this
user.
is bounded, we can
I think
avoid,
that's going to be too difficult for me to
Indeed.
whatever.
put
That's
across.
This
what I
K
wanted
is a
audio.
function that is chosen by the user.
Yeah, it's strange that the audio doesn't work, but let's first inform them that the audio doesn't work. I will type
this
that.
binder induction method, depending on what the user put here. So this K function is exactly the function that extracts all the free variables from gamma prime. And this row parameter will just be gamma prime, because we only have put one thing here. If we put multiple things here, this would be a tuple of all the things we want to avoid. That is roughly how that works. Okay, I can hear, but I don't think, can I have audio?
I'm speaking right now, but I don't think you could. Do you hear what I'm
Sorry,
saying? Jan?
I have muted my audio, maybe that, because I don't want. I think we cannot hear them. Yeah.
Can you hear me speak now?
Yes.
Okay, now Jamie, you go ahead, because I didn't have a question. Jamie did.
Yeah, thank you very much. Hello, Jan. Jan,
Hello.
thank you. I've been listening with tremendous interest. So I asked if you could give a flavor for where the additional freshness assumptions came from. And your answer, as I understand it, was, well, we just asked the user to prove equivariance. Have I understood correctly?
Basically, yes.
So
because with those we can prove this. So I can show you, actually, I can show you the default.
I seem to be trapped on the, I can't, yeah, okay.
Yeah. I can show you the whole proof of the theorem. So I have, as I said, the automation is not fully working yet, but
Jan, hold on.
Yeah.
So the key point here is that the user is expected to provide an equivariance proof. And with that input from the user, the system can then proceed to rename a possibly fresh name, rename a possibly stale name so that it's fresher.
Exactly.
That's perfect. I understand that. I wrote a paper which perhaps you should look at called Equivariant ZFA and the Foundations of Nominal Techniques, in which I talk about equivariance. My concern would be that equivariance is a bit that's hard. Do you have any comment on that?
It depends on what. So the user will not need to prove equivariance about the relation. What the user will need to provide is only for all the other functions they use within the relation. So in this case here, the user will need to prove, let's go here. So need to prove equivariance for not in, which I assume would also be in the standard library, because I can just build a database of equivariance proofs. Same with the cons operator and so on. So, but these are the only two functions I see. Oh, lookup is also a function. But if you prove for these three, that is enough.
Okay, that answers my question. Thank you.
Yeah, all the other proofs can be completely automated with that knowledge. All right, then I will go back.
Thank you.
All right. So, yeah. As I said, the final goal is, if I have time, to implement this in GHC. For that purpose, I will visit a GHC workshop with in the summer, get into the GHC code base a bit. So, just, yeah.
Julian wants to ask something.
Let me go.
No, not anymore.
You need to change text to the
Yes, to here.
Julian.
I don't have any other questions. It was just that I was contacted by Jamie that he could not make himself heard.
Okay, yeah.
And I kind of bridged the gap between you and Jamie, and now you can just continue.
All right. Yeah, I don't want to turn on audio on this machine because I know it will loop back with the microphone of the other machine. So yeah. So the implementation status of all this, basically during my masters, it was during that. We have composition algorithm that builds on this general axiomatization. So when I say axiomatization, I mean basically you give me some constants and some proofs about these constants, and I will give you back some other proofs derived from these axioms. There is no new axioms that are introduced. It's just like the axiomatization refers to the fact that you need to prove some facts about your constants. Then this was again, as I said, done by the different students, and I just integrated that. But building on top of that, I built this recursor, the fold on the data type that you get. And the thing I said earlier is missing is the co-recursor, so the unfold of the data type, if it's a co-data type. But what is working indeed is the temporal and variable substitution, and just some general stats. So yeah, high-level sugar is that I can abstract it. That's more or less done now. I only count the binder inductive there as well, and of course the parser. So this is a bit outdated. I think we are at 15,000 lines of code now, and that is just the code in the repository. So this is not including all the data type code that we partly reuse that is already in Isabelle. And yeah, as this was another student here. This was mostly done by the original people, and then yeah, the rest is written by me. So to summarize all of this, I'm working on this because I want row types in Haskell. So far, we have almost usable or very close to usable tool in Isabelle. It is not that hard to use even at the current stage. I want to submit a few papers and finally implement these rows in GHC. And this implementation at the moment is more or less complete for data types. It's still missing the co-data type part, but most syntaxes are just data types, so that is already a very useful thing. And also, as we see this as a generalization or improvement of nominal 2, Normal 2 doesn't support this either, so everything we do is already better than what was before. Yeah, now I will change back so I can get questions that are beyond this, or if there's anything left. Does anyone have questions about this or anything? Let's see.
Hi, Jan. One quick question from me, if there's no one else.
Yeah.
So I seem to recall in the first example, you showed us the example where you type checked a bit of a code, right? With a lambda abstraction. The lambda abstraction, the variable names in the Isabelle code seemed to be like have question marks before them. And is this like a special syntactic treatment that you have for bound variables?
No. I can show you this very quickly.
Yeah.
So in here in Isabelle, let me go to the theorem you went in Isabelle.
Yeah, that's one. Yeah.
Below it, this question mark x, or this is a schematic variable, which just means you can put any term in there with unification. The reason why it is so bad, because Isabelle generalizes, so I gave it with some fixed x, and Isabelle after the proof generalizes the theorem, so it works for anything you put in there of the right type, of course.
Right, so it's basically universally quantified name.
I could also, if I with like I need to would need to add a small proof, because there's a type class involved. So let's just let's use natural numbers for these things. This should be then that is to be improved. So with this magic line, I can also put 0 here and use 0 as variable name, and then the whole proof, of course, is not a variable anymore. So it's not a schematic variable anymore, and so you can't put anything in there. The same is happening in the, for example, in here in the set function. So this can be any term that has the right type. Especially this thing can be any expression that you can. So that this is for unification. Unification can only happen in schematic variables.
Yes, that is roughly what I would expect. So I was a little bit surprised to see the question mark there, but yeah, that does make sense. Thank you.
Other questions? Yes.
So in your examples, you seem to use a mixture of the technical language, so the LAIV, and I think it's the Isabelle language for register.
Yeah. So
impact on the proof automation, or is that
no? So in fact, either is so I used by in the either proof. By is simply a shorthand for apply and done. So this the only reason why you can apply to for example is because I manually did all the rules. In fact, because I added the introduction, I let the automation know about this. This whole proof could be done by auto without issue. I just to show it's nice because you can see in every line what is happening. But in general, you saw like the actual theorem I proved was in ESA, because usually that is way easier to read as a user than an apply script, because you do not need to click at every line to see what the current state is. So yeah, as a user, you would generally want ESA, but that is more or less a preference thing. So it's not more or less powerful. Also, this binder induction is another. You can also apply binder induction with the same arguments and then get a bunch of goals that happen to correspond to this. It's just nicer to read and nicer to work with in ESA style. So in a nice structured way. But yes, it's basically it's just syntax sugar for apply scripts in the end. All right. Then if there are no other questions, thank you everyone for listening. And yeah.
Thank you very much.